Hello there. In this lesson, we're going to look at the equilibrium that exists between a precipitate and a saturated solution. So whenever you have a precipitate or a solid that cannot dissolve anymore into a solution, there is an equilibrium that exists between the two of them. And these are quite common. It's like a whole sort of subsection of equilibrium. So that's what we're going to look at in this section. All right, when you first add a solute to a solvent, like these crystals of some copper compound in water, then they'll start to dissociate. The ions will start to come apart and it will dissolve into the solution. What also happens is that if the oppositely charged ions come in contact with each other, you'll start to get a little bit of recrystallization. So that process increases as you dissolve more and more into the solution. Well, then more and more particles will be free to start to recrystallize until eventually you get to a point where the rate of dissolving or dissociating is the same as the rate of recrystallization, and that would be your saturation point for that given temperature. And so that's when you have an equilibrium, is when the solution is saturated. The solubility is a term for the maximum amount of solute that can be dissolved in a given volume at a certain temperature. Obviously, it changes with temperature. You know that when you increase the temperature, more will be able to dissolve, and the opposite when it gets cooler. Solubility can sometimes be expressed in terms of grams per liter, but we're going to mostly use it in moles per liter, so it's important you be able to convert from one to the other. So if you want moles per liter and you have the 730 grams per liter, you can always convert that by using the molar mass. So this is copper to chloride with a molar mass of 134.5 grams per mole. And so you can put your 134.5 grams for every 1 mole and have it work out so that the grams cancel out, and you'll end up with your concentration in moles per liter. So 730 divided by 134.5 is, and they end up with, oh, it's pretty high concentration, 5.4 moles per liter, or the big M means moles per liter too. So once an equilibrium has been established where the solute is dissolving at the same rate as it's recrystallizing, you will have an equilibrium. And of course, with that equilibrium, you have a constant. This type of constant is called a solubility product, or KSP, and that is because it's heterogeneous. And so the part that's a solid, the precipitate, or the part that was undissolved, is left out of the equilibrium expression, and it'll be just the ions that are dissolved in the solution. So for example, here with copper to chloride, you're going to have some copper ions, and you're going to have some chlorine ions. You'll get 2 chlorine ions, of course, for every one of the copper ones. And so the concentration of copper ions times the concentration of the chlorine ions squared would be the equilibrium expression, or KSP, for that compound. So a few simple equilibrium constant problems relating to solubility. If we have the solubility, the amount of the solid that will dissolve at a given temperature, you can always work out the KSP for that. And so we know that lead chromate here, CrO4, it's lead 4 chromate, is gonna create an equilibrium where you're gonna have the lead, and you're gonna have 2 of these CrO4 ions, so that'd be A2 minus, and so your KSP then is going to be the concentration of the lead 4 plus times the concentration of the chromate squared. So we need the concentration of those two, and so this is the solubility. This is how much of this whole compound will dissolve, and so you see that you're going to get twice as many chromates as you will leads when that dissolves. So you'll have the 4.5 times 10 to the negative 5 moles per liter for the lead, but you'll have double that for the chromate, so it'll be 2 times 4.5 times 10 to the negative 5 moles per liter for the chromate. So you can put those values in here, and we can solve for the KSP. So the KSP here is going to equal 4.5 times 10 to the negative 5 moles per liter. You multiply that by 9.0 times 10 to the negative 5 moles per liter, and that one will be squared. So we'll put that in our calculator here. 4.5 times 10 to the negative 5 times 9.0 times 10 to the negative 5 squared equals. So I get 3.6 times 10 to the negative 13. Yeah, some of these equilibrium KSPs can be very small. All right, so using an even smaller one, we're given the KSP and we want to find the solubility. So if you want to go in the reverse, you can do it like a little ice table. It can be helpful, right? So we've got our copper 2 hydroxide this time, and it's going to form an equilibrium. Of course, we're going to have the copper 2, and you're going to have hydroxide ions, 2 of those, and so you initially put in X, you're going to get X amount of that, and you're going to get 2X amount of this, right? And so your KSP is going to be the product of those two, this concentration times this concentration squared. So the X is, the 2X squared is going to be 4X squared times X will be 4X to the power of 3. And our KSP here is 2.2 times 10 to the negative 20. And so we'll go up here, we'll divide that by 4, so 2.2 times 10 to the negative 20 divided by 4 equals, oh, of course, we have 5.5 times 10 to the negative 21 equals x cubed. And then we'll take the cube root of that, and I end up with x being 1.8 times 10 to the negative 7 moles per liter. So that would be your solubility, right? Because that's going to be the amount of this whole compound that can dissolve. Yeah, so there you go. If you can solve for x, you've got the solubility. Our equilibrium quotient, or Q, that we used earlier to determine the direction of shift for reaction to get to equilibrium, can also help you in determining whether or not you get a precipitate, because a precipitate is the solid that's on the left-hand side. And so if you have starting concentrations that give you a value that's below the KSP, well, then it's going to shift this way, which means everything's going to dissolve. If the Q and the K are the same, that means you're at equilibrium and you're going to get equal movement in both directions. And if Q is larger than K, that means it's going to shift this way, and this is where you have your solid, so that means you're going to get a precipitate. So it's like a quick way to tell whether something's going to precipitate or not. Alrighty, so let's have a look and see if we'll get a precipitate here or not. The equilibrium KSP for this is going to be the concentration of the copper ions times the concentration of the chlorine ions squared. So we have the KSP, and we just want to work out Q. So Q is going to be 0.025 moles per liter for the copper ions times 0.015 moles per liter squared for the chlorine ions. And so if you multiply those together, 0.025 times 0.015 squared equals, you end up with 5.6 times 10 to the negative 6. And so I'm going to compare that to K. So we got Q and we got K. So Q is 5.6 times 10 to the negative 6, and K is 5.5 times 10 to the negative 6. So that means that Q wins. We're going to shift in this direction, which means we'll get a precipitate. Precipitate forms. Yay. You can see they're very close though, so it wouldn't be a lot of precipitate. You can just get a little weeny shift and then you'd be at equilibrium. So it might turn cloudy or just have a tiny bit of fragments that would sink to the bottom. Okay, the last situation we're going to look at here is when you have ions already in solution that are part of your solute. And so our first example here is we got copper chloride and it's dissolving into a solution that already has some sodium chloride in it. So the sodium is not going to interfere with anything, that's no problem. But the chlorine is what you call a common ion because it is in both of those compounds and already present in the solution. So we have a couple more examples over here. The first one is the one that was illustrated. You see that the chlorine is the common ion that is already in the solution and it isn't the thing that's trying to dissolve. And for the second one, if we dissolve copper chloride in a solution that has some copper sulfate in it, well, then it's the copper ions that are the common ions and are already present in the solution to some extent. So there's an effect that happens when ions are already present, common ions, to both the solute and in the solution. So, ta-da, the common ion effect is that if there are common ions, that the solubility of the thing you're trying to dissolve is going to be reduced. Less of it will be able to dissolve because there's ions already present in solution. So if you have common ions, like the situation here on the right, the solubility of copper chloride in that solution is going to be less than if it was just pure water or the ions in there weren't copper or chlorine, right? So you should be able to dissolve more copper chloride in a solution of pure water than one that has some common ions present in it. So to make calculations based on that, you just have to make yourself a little ice table and put in the common ion concentrations as an initial concentration. So if we're looking for calcium chloride here, how much could dissolve into a solution? So we're going to end up with calcium ions, and end up with chlorine ions, 2 of those, and so this is going to go up by, initially you would have no calcium ions, but there's already these common ions, this chlorine from the sodium chloride that's already present. So you put a 0.025 moles per liter in there for the chlorine initially. And then the change, of course, will be the same as usual. You're going to gain some x there, and you're going to gain 2x here. And at equilibrium, you're going to end up with x, and you're going to end up with 0.025 plus 2x. And so in order to solve this, your KSP is going to equal x times the 0.025 plus 2x. And that'll be squared. So that'll be a pain to solve, right? So we can use one of our simplifying assumptions here. These values for the constant are very small, which means the shift here is also going to be a very small shift as well. So this is one of those situations where we're very close to the equilibrium quantities, and so the shift will be small compared to what you start with. So we can make this negligible and just solve for this x over here to figure out what the small value is. So that makes it a lot simpler. So you end up with the 4.4 times 10 to the negative 9 over here. We have the x, and we have 0.025 squared. And so we can solve for x pretty easily just by dividing 10 to the negative 9 by the 0.025 squared. So let's do that. 4.4 times 10 to the negative 9 divided by 0.025 squared equals. And so x, as expected, is a really tiny value. 7.0 times 10 to the negative 6 moles per liter. So that'd be your solubility in this solution that already has some chlorine ions in it. All right, there you go. Hope you learned something about solubility equilibrium. We'll see you soon.